Good morning, everybody. This is Mark Anderson. I'm with Staddies Incorporated, Minneapolis. I'm going to talk to you about optimal experiment designs that combine mixture, process, and categorical inputs. Some of you may know, since I've been with Staddies since the beginning in 1982 when we were set up as a company in the state of Minnesota. And really before that, now is actually 50 years of working on design of experiments, starting as a summer engineer with General Mills Chemical in Minneapolis. I have a great deal of experience as a professional chemical engineer, PE, and certified quality engineer working in manufacturing process improvement. And then I do also have my MBA and was running Staddies for many years, but then several years ago went to a 60% role and strictly technical as an engineering consultant. So I've come full circle, but I'm really happy to be able to devote all of my 60% of time to try to help people get started with design of experiments in general, and then get into the more complicated type of structures like we see here that incorporate both the process, which is represented by the cube, and this would be a two-level design with three factors, would be the cubical part of this little diagram. And then the triangles, as many of you may know, are representing mixture experiments. In this case, the triangle represents three components in a mixture. And we would say that Q is equal to 3 in a case like this. All right, and then together, we're combining these and forming an optimal structure that allows you to more or less mix your cake and bake it too, and then perhaps even work in categorical inputs like, do we bake it in an electric oven or a gas oven? And so that would add one more dimension to this whole structure. And this is very common for any of the process industries. The chemical, I mentioned I worked in specialty chemical process development, pharmaceutical, paints, of course, foods, cosmetics, all kinds of things where not only is it the formulation that matters, but also how you process it, and perhaps also, some categorical inputs like which supplier do you use or which chemical do you use. So again, I want to welcome everybody. I believe that you're all on mute at this point automatically, and I'm not going to mess with the controls at this point. Chat could be addressed afterward, but I think I'm going to say no to that and ask you to send further questions to mark@staddies.com, questions that you build up along the way, and then after the end, if you would please send those to mark@staddies.com. That'll probably be best since we're recording this, and so that this will be available on the YouTube. You'll find the YouTube if you follow through the webinars page, and then from there, there'll be a link to the YouTube video. And this might be a good way for you to review. Some of you are watching this for the first time on YouTube, since this will have a life of its own going forward after this. So in this presentation, I hope to provide practical aspects that combine mixture, process, and categorical variables into one optimal experiment design. And then how to do this with a minimum number of runs via a very clever KCV, quote unquote, which is named for Kowalski, Cornell and Vining combined model. So this is going to be a specialized model geared, to these combined designs. And then some details for structuring these designs into a split plot, which allows them to be far more doable by dealing with what are called hard to change factors. And for example, kind of a really common issue with these combined designs is oven temperature, is not something that you can easily randomize. So we're going to combine those. So hopefully by attending this webinar, you'll be expanding your horizons, deploying DOE into structures that simultaneously optimize product and process improvement. Okay, and then what we'll do is we'll hang some ideas off of several different case studies. The basic idea of mixture process experiments, which is the fundamental combined experiment, and then the different models that you can apply, which would be the old-fashioned crossed models that are more of a brute force approach versus these more elegant KCV models that'll minimize runs and still preserve the advantage of looking for mixture versus process combinations of things. And we have a case study that probably some of you have heard about, fried fish patties for a fast food sandwich. And this comes from John Cornell out of University of Florida in Gainesville, who did the foundational work to bring mixture design to industrial researchers. And then the idea of the split plot designs is going to be a much more advanced idea, but it's very useful, and we'll show you a case study on making chocolate chip cookies, something you could try at home. You could try the fish patties also. However, that might be a little bit more work and not as much fun as chocolate chip cookies. And then including categorical factors, we'll talk about a composite material case. And I'm just going to say if time allows, because I'm trying to stay within the 1 hour time frame. But at least I'll bring this up and you'll see the basic idea of it. And then finally, the conclusion. And then Q&A, I'm going to say, let's email. And again, I'm Mark, and I'm at statease.com. Okay, so far, if you're good with that, do that raise hand thing again. And I want to see if that shows up on the screen. There we go. Okay. I've got the usual 3 suspects at the top, plus 4 more that came in. So thank you. Keep responding as I ask you along the way. That'll give me some positive feedback. And it also helps me to make sure that everything's working great on the audio visual across the internet. We do have a little storm that's going right now here in my home office in Stillwater, Minnesota. And so you never know what might happen. Okay, so now let's talk about the geometry of these mixture process designs. And these are very interesting combinations of things where we talk about the design space for a mixture, for example, forming Q components minus 1 because of the total constraint is fixed at, let's say, 100 weight percent. Once you know any 2 out of 3 ingredients, the third is fixed. And so we lose a dimension. And we form what's called a simplex geometry, which for 3 ingredients is an equilateral triangle shown here at one end of this prismatic shape. All right. Now we're superimposing a process factors, which we're calling Z, and this creates a dimension going from left to right. And this is coded from -1 in process space to +1, where -1 would be the low level and +1 would be the high level, for example. It could go the other way, but we generally recommend making the -1 the low level of a numeric factor and the +1 the high level. Now, for the mixture space, the coding is going from 0 for each ingredient up to 1 from the bottom to the top of the triangle, for example, for x sub 1, and then going from right to left for x sub 2, it's going from 0 at the right side to 1 at the left corner, and then component 3 is going from 0 at the left side to 1 at the right corner or vertex. And by the way, this particular layout also works for mixture amount experiments, and that's an important variation on combined design. Typically, we assume for a mixture that the impact is due only to the proportion of the ingredients and not the amount. And that might be true for certain things like the electrolytic properties of some kind of mixture of water, with ions. But for other types of things like coatings, it's not only the composition of the coating, but also how many applications of the coating you put on. So amount does matter in some cases, and we can easily accommodate that with this combination of mixture and process, where process factor is really an amount. All right, now the layout of this particular structure that we're showing here with the overall centroid shown in the mixture space, the binary blends, which are the sides of the edges, and the complete blends, which are the pure blends at the corners. We then have enough data to provide what's called a special cubic mixture model that was invented by Chaffee in the 1950s. And these are specialized models that are different than the typical ones you see for processors. No intercept. We look at the relative main component effects with the first part of it, which is the linear part. And then the second part, which looks kind of like interactions in a process, really is much more than that. And it actually gives you what's called quadratic impact or nonlinear blending. And then finally, we have a three-part term, and this would show the combination of three things having an impact. And this is the special cubic term over here. And with that, we've used up all the information that we have from the 7 points in the design. Now we're crossing that with a simple model that's just a standard linear model that has the slope, alpha 1, and the intercept, alpha naught. So there's 2 terms in that model. There's 7 terms in the mixture model, 2 in the process model. And then combining those all together, we end up with 14 terms. So this is what's called a cross model. And this is for 3 components and 1 process factor or amount. Now, adding on to this, we could go to a second process factor. And in that case, then now we form a square, and we've got triangles at the corner. Alternatively, we could show triangles with squares at the corners of the triangles. Either way, we've got still the special cubic model, right, with the 7 terms. But now for the process model, we've added in a second main effect, and then also the interaction of the 2 process factors. Now we've got 1, 2, 3, 4 terms, and so now we have 28 terms to deal with. That's a lot. Already we're getting, kind of out of hand here with the amount of terms that we have. And now if we go to a third process factor, well, it's kind of getting to be too much. Because in this case, now we've got still the mixture model with the 7 terms, I think it was. And now we've got the quadratic term, and we've got a total of 56 terms. So that's getting to be too much. So what we're going to do is take a look at a possibility of reducing that down. All right, so let's talk about a good compromise for mixture process designs, and introduce this idea that was presented by Kowalski, Cornell, and Vining, which we call the KCV model. All right, and so what we're going to do then is we're going to create a hybrid model that doesn't cross all of the terms, but only the linear model terms. And that way we preserve the ability to be able to detect combinations of process and mixture, but without going, into crazy large terms like 6-order terms that we saw in the last example. So this makes the mixture process combined designs far more practical. And it now is the default that we give in StatE software for that reason, because of it being much more practical, and we can allow then more mixture components and more process factors by using this KCV model and still preserve the advantages. Okay, so let's look at a completely crossed versus a KCV model. The completely crossed model for quadratic by quadratic, for example, with 3 components and 2 process factors, generates 36 combinations. So we've got 3 components and 2 process factors. We're looking at a quadratic model by quadratic model. And so for the mixture model, we've got the 3 main component effects. We've got the 1, 2, 3, 4, 5, 6, 7, 8. We've got 1 combination of A and B component, 1 combination of B and C, and 1 combination of C and D. So this is the quadratic of the mixture. And then these terms, NAC also, these terms that involve the process factors which are D and E, are going to give you the combination of, let's say component A with factor D, component A with factor E, and so forth like that. So that's where these two terms have gone. They've been crossed with the three mixture components, and they're showing up down here where these green check marks are. But then we get into, higher order terms, and it keeps building up more and more, all the way up to, let's see, we've got a whole series of third order terms here that are building up on this little screenshot here. All right, and then we have, we've got fourth order terms now, because we've got the nonlinear blending term AB crossed with the interaction of DE, and so it's getting, worse and worse, all the way up to fourth order. So here's the fourth order, third order, and the first and second order. That's a lot. And it turns out that these high order terms, let's say certainly the third and fourth order terms, will almost certainly be insignificant. So we're spending effort to generate degrees of freedom to estimate those terms that are a waste. Now for the same example with 3 components and 2 process factors, the KCV model only needs 15 coefficients, because it does give you the quadratic mixture AB, AC, BC, DE. It gives you the quadratic process, but not crossed with the mixture. And then it gives you simply the linear mixture terms crossed with the linear process terms, and nothing else. So in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Much more elegant. And yet it preserves the combination terms that we see here in the red squares. That gives us that necessary, the whole reason of doing the combined design is to try to see if there's a combination of how you mix something with how you process it, or vice versa. That's why you're doing the combined design in the first place. All right, so again, I'm just going to ask you if you're with me so far, and you can see some advantages here to reducing to just this combination of the linear mixture and linear process. If that appeals to you, press that raise hand button. Okay, and a bunch of people have raised their hand. I can see that on my control panel, so thank you for the positive feedback. All right, so now this table is kind of a sell sheet to sell the idea of doing the KCV model, because as the number of mixture components and process factors goes up, the cross model starts to explode, in terms of how many terms there are and how many runs therefore you need. And if you look at the KCV model, you can see that it remains fairly reasonable, all the way up to a fairly large number of mixture and process factors. Now, generally speaking, I would suggest that for a process study, you would do at least 8 runs, for a mixture at least 12 runs, because of the collinearity. And so there is an issue with power. And actually, we use what's called fraction of design space, and we look at precision as a metric to size these designs, but it's a similar concept. And certainly, for a little situation like this where you only have 2 mixture components and 2 process factors, you might just go for that crossed, model of quadratic by quadratic. But as soon as you get into 3 mixture components, you're already up to 36 terms with only 2 process factors. So I think I would start to work with the KCV and shift over, and don't do this crossed, model anymore. All right, so let's take a look at an example with fish patties. And this one, the story goes from Jeff Vining, who gave us some history on this, that his graduate student Kowalski and Jeff Vining, as a supervising professor, started to work on this idea of a more elegant model. And they enlisted John Cornell, who was the guru of mixture design. And together they formed this idea. And then what we've done is we've paid homage to Cornell and an experiment he did with his graduate researchers down in Gainesville with some really unusual fish from Florida that I'm familiar with, having a winter home down in Venice on the Gulf Coast. mullet, which actually is looking like kind of the zebrafish and has a very strange mouthful of teeth. Believe me, you don't want to see it. Sheep's head and croaker, and I'm not sure which one's the sheep's head and which one's the croaker. I've kind of lost track of that. I've just seen people fishing off the jetty, and most often I see them catching these mullet. But evidently, they're quite tasty, and sometimes a combination of things can be more tasty than any one alone. And so these are our three fish that are going to be used to make this fish sandwich by Burger King called the Whaler. And then there's three process factors: oven temperature, going from a low to a high, time in the oven from low to high time, and then deep frying. Of course, we want to do that for our fast food to get it to be really tasty, and there's a range of time on that. Now, this particular study, let's assume that the fish are going to taste good, and we're really focusing on a difficult attribute, which is to get the texture to within the specification. So it's very important to get that texture and specification, and that's what the focus is for this combined experiment. Okay, so now we see a layout, and this is actually a cross design that does all the possible combinations of the full factorial on the process factors. And you can see that this is in what's called standard order because of the way that the pattern is going low, high in the first column, and then two lows and two highs in the second column. And of course, what we want to do is a completely randomized run of all these combinations of things, but it's convenient to tabulate it in the standard order. All right, so there's 8 combinations of the process that are shown on the left side. Now, on the right side is a design that's called a simplex centroid. It's kind of an old school design. It's a textbook design that was written up in John Cornell's Experiments with Mixtures. And the idea of it is that you always end up with one complete 3-part blend, or the centroid would be here at the end. All right, and then we've got the pure blends, which is kind of an oxymoron because they're not blends, but we've got the pure amount of fish number 1, the pure amount of fish number 2, fish number 3, which are the sheep's head, the mullet, and the croaker. I forget which is which. We've got binary blends of each of the 2 fishes, and then again, the overall centroid. Now the goal was 2 to 3.5. And so in a randomized plan, they did all these possible combinations of process and mixture. And then it's always good, I think, to eyeball the data. And I heard Montgomery refer to this as the intraocular test. So intraocular test is another way of referring to this. So in this experiment, then, we have some combinations that fit above 2 and fall below 3.5, and we could just maybe circle some things here, and we can see some promise because some of the results do fit into the specification range and some do not, which is kind of an ideal situation, right? Because if we get a range of response that goes from below spec to above spec and has some in spec, we've kind of captured the whole problem within that data set. And then it's just a matter of checking to be sure that this is a significant outcome. But already it seems pretty promising, that we're going to get something significant out of this. So I like to just eyeball this data. Now, the thing about this is that it's a lot of work. And if you were a fairly high-powered professor who was an expert in his field, you might have a fairly good core of graduate students that could do all this. But in industrial research, like working for a food company, you're probably not going to be able to afford doing all these possible combinations. So this is where the more elegant approach comes in. And so we just took the results from the original study from Cornell's book. That gave us a model, and then we simulated from the original experiment what would happen if we were able to do this over using the KCV and using a computer optimal design. So this will produce a model with only 21 terms as opposed to 56, which means we only really need to do 21 combinations. And yet it preserves that ability to model the process factors all the way up to quadratic, and it preserves the mixture process interactions. Now we bolstered this KCV model with 5 additional unique points to fill in spaces in the design of the 21. And then we replicated 5 of those 26 using optimal design for a total of 31, which is still a far more manageable number. And actually, the original design that we see here doesn't have replicates, so it doesn't estimate pure error, and therefore we can't get the lack of fit test. So I'm now going to toggle over, and I'm going to go to the Design Expert software. Actually, I'm going to use a more advanced package called States 360 that incorporates the Design Expert. And the only difference of the States 360 from the Design Expert is that it adds in the primary advantage is something called a Python script editor that goes out and brings in some things that you can combine with the Design Expert engine and do some new things. It also has some designs that we won't get into here, which are called space filling designs, which are very specialized for doing experiments on a simulator, and particularly where the simulations are deterministic. So those are things that we're not going to look at. And instead, what I'm going to do is go ahead and open up a design called fish. All right, so let's find that. And we'll pull that up. And here it is. Okay, so what we have is a design that is in random order, and it's varying the composition of the mullet, sheepshead, and croaker. And then it's giving differing oven temperature, oven time, and deep fry, and then the texture is being measured. Now, the way this is built, I'll show you by rebuilding it, is using optimal combined design tool in States 360, but it would be the same thing in Design Expert. And of course, we've got 3 mixture components. We've got 3 numeric factors. And then it's a matter of simply entering in, what you're working with, and you could put in certain constraints here if you would like, individual constraints, and even you could put in what's called multi-component constraints. But we're just simply going to allow this to go from 0 to 100, so it's a fairly straightforward design. And then we put in the process factors, which are the temperature, time, deep fry. For the moment, we're leaving these all as easy to change. We're not introducing the split plot yet. And then we get this control panel, which I don't want to get into in any great detail, but you want to study, the principles of optimal design. We're using something called I-optimality, which is common for response surface type work that you're doing in process or mixture or both. And then you can see here is where the KCV model is picked, by default. And this is generating 21 terms, which are going to give you 21 required model points. And if we had gone back to the quadratic by quadratic, well, then the number of required model points would be 60. So we don't want to do that. So going back to the KCV, which is an elegant hybrid that only includes crossing of the main component and main process factor terms, and leaves the pure quadratic mixture and process alone, and that allows us to reduce the number of required model points. And then you see lack of fit and replicate points are added in for a total of 31. Now, if you have any questions, remember mark@states.com on some of the details of as we go along here. Feel free to shoot those into me. Now, we're only focusing on one response, which is the average texture. And now we're going to go ahead and let the program do the optimal design algorithm. And it might take a little bit of time here. And then it lays it out. Now, this happens to be done, there's an option of either coordinate exchange, which can give you these odd decimal place numbers, or sometimes it might, on a few occasions, pick something called point exchange, which is more geometrically registered. But most of the time, it ends up getting a more optimal selection from coordinate exchange. So what I suggest you would do is that you would round this before you would run this, and maybe we would round the mixture components to 1 decimal point to make it easier for the people running this to mix this up. It'll make it a little less optimal, but not very much. And then we could also round, the individual numeric factors very readily using this tool, which I really like. And this would be, a more doable design, slightly off optimal at this point, but not that much, and probably worth it to make it a more practical deal. So now, though, I'm just going to go ahead and open up the original file that I had, and then you can see the textures over here. Now, the analysis of this gets a little bit complicated. I really am wanting to focus on the design of the experiment and not so much the analysis of it. But suffice it to say that we've got tools in the software that will help you not to overfit the data. But what I would suggest is that we would just go with the KCV model in a case like this to start with, because that's what we designed the data to fit that KCV model. And then we could look at various p-values and try to assess what's going on. But what I recommend we do with these combined models, even with KCV, there's still a lot of terms and many of them will be insignificant. I really like doing this automatic model selection, and I prefer the old-fashioned p-value backward approach because it's easier to explain that what the algorithm will do in a hierarchical way is take out terms that have very high p-values and then refit as it takes each one out until it no longer finds any according to the criteria you've got here, which is an alpha of 0.1 or 10% risk. And then accept that, and it might do some hierarchical adjustment. But what happens in this case is we end up with a very nice model, very elegant KCV. Even further elegance is introduced by reducing out the insignificant terms and yet maintaining hierarchy. And we end up with really good properties in terms of the fit, namely the predicted R squared is very, very good. And so then I would just look at diagnostics and make sure there's nothing abnormal in terms of the normal plot of residuals. I would look at the potential of outliers if this is a real experiment, looking at residuals versus run. And then I always look at the box-Cox plot to see if there's a transformation recommended. And in this case, there isn't. Then we get into all kinds of hair-raising analysis, trying to see if we can stay between the 2 to 3.5. And it turns out that at certain conditions of processing at the high oven temperature, high oven time, the deep fried time doesn't really matter as much. We end up with a good sweet spot, where we get a zone that's between 2 and 3.5. And so 2 and 3.5 is our goal, and we get a good, swath of mixtures that we can make of the fish that will meet that. And then you can get into all kinds of numeric optimization in this case. So by setting a goal of 2.75, halfway between 2 and 3.5, we can begin to look for solutions that meet our requirements. And this is where we can begin to impose, further requirements. In this case, the sheep's head has been set to maximize because of its being so cheap that day. And so that's why it's got this upward bar on it. So this is a scenario where we want to maximize the sheep's head because it's cheap. And then we also notice on this dot plot that we set a requirement on oven time, which is a productivity situation, to be minimized. And so this is a very particular set of requirements in our optimization that not only takes into account meeting the specification, but also that we want to maximize the cheap fish and we want to reduce the time. And you can see the end result of this was we didn't hit the target exactly on at 2.75, but we were well within the spec range. So this is a very satisfying outcome, and it's all done with a very elegant design called the KCV that doesn't have nearly as many runs as a cross model. All right, that's about all I'm going to say at this point. But if you're impressed by this outcome, put the raise hand button on your control panel. All right, and thank you again, for your participation on this. Okay, as I said, there's a lot of material here, so I've had to kind of, press through this a little bit. And here's the requirements that the sheep set would be maximized that I demonstrated for you that I added in. Um, I didn't mention that I also had an equality constraint because Croker, we wanted to get as much as we could get in, which was enough to get 15% of production. And then the faster food by minimizing the oven time, I showed you that. Okay, now the remaining time, I'm going to buzz through this a little bit, but there is another presentation on the chocolate chip cookies that you can get from our YouTube channel that I did for one of our DOE Summit presentations. So you could go back and look for that. But the story is that Greg Hutto, who is an adjunct professor, he's actually based on Eglin Air Force Base in Florida, and they've got a campus there for University of Arkansas, and he does some teaching of industrial engineering. He had an adult student, Jessica Keel, who, as a project for his DOE class, decided to use this cakey chocolate chip cookie recipe from Martha Stewart and see what would happen if she varied the relative amounts of butter, granulated and brown sugar, which was a multi-component constraint, using one and or the other, and then vanilla, and then baking at different times the temperature. And this was the mother of all designed experiments. And Greg was a little daunted by that, so he enlisted me to help him with this because it was mixture process. We used the KCV modeling, but it also involved something called a split plot because of the factors being hard to change, particularly the oven temperature and time was going to be harder. So it was much simpler to make a tray full of cookies with varying ingredients and then bake them all at once at varying times and temperatures. And this was a grouping that creates a specialized structure called a split plot. And this is oftentimes, useful, particularly for combined designs that a complete randomization is not practical. So we need to restrict that and yet do it in a way that preserves some ability to deal with the restriction and the reduction in the significance that's going to occur because of the non-randomization. So you have to be very careful in setting up these split plots. You're going to pay a price on whatever you restrict on randomization, in this case, the process factors. This split plot originated way back when, I think even going back to the days of Fisher and his work on inventing DOE for agronomy. And one classic example is you're going to spray a herbicide and you can't, do it so narrowly when you take the path to get over each strip of the different types of the plants that you're planting. So what they do is they, in their airplane, and this is supposed to be an airplane, but I know it's pretty bad. But in that airplane is a tank, and the pilot's going to switch over randomly according to the plan to different herbicides, and then he's going to spray across these subplots that are also randomly applied before flying back around and switching the tank by the random plan back to a second herbicide, spraying across all three subplots in this whole plot, and it goes like that. So this is an area that, again, you would want to study, but my tip is that the combined designs are going to be ones that you might seriously consider also applying a split plot structure to. And that's what Jessica did in her case. Now, there's actually two different ways we can go. The way that Jessica went, which is probably going to be more common for the baking, is making the process factors hard to change. And then mixing each cookie at random. So each one of these individual cookies on the tray are mixed by different compositions, but then they're baked out at whatever time and temperature is indicated by your random plan. All right, so I like to draw this structure with the square with the triangles at the corners. Now, on the other hand, we could make a huge batch of cookies according to one recipe that we pick out at random. And then we could bake one cookie at a time, but that would really only work if you had a specialized little one cookie baker And we happen to have one here at the Anderson household in Stillwater. It's called an Easy Bake Oven. You may remember this from way back when you were a kid, but it's got a light bulb in it, and the kids can mix up a little cookie and put one cookie in the oven, turn on this Easy Bake Oven, and the light forms the heat, and then you could bake that. Now that would also be a split plot, but we're now making the mixture components the hard to change, and we're making the process factors easy to change because of this Easy Bake Oven. And here's a picture of the Easy Bake Oven that's just on the other side of the wall from my home office here. And we've got that squirreled away in the bottom of one of the drawers. I haven't tried that. I don't think that this is the way to go, using the Easy Bake Oven. I think using the regular oven and then doing what Jessica did is making a whole series of cookies that are randomly mixed up according to your plan, and then baking them out at a specific time and temperature is the way to go. So all I'm going to do with this one is I'm going to open up the chocolate chip cookies file just to show you the grouping. And so let's open that up. And I won't try to rebuild this because it takes like all night to build this, because not only was it grouped by the time and temperature. So here you see one grouping of 3 cookies that baked at 325 at 18 minutes or whatever. And so here are the randomized 3 cookies that were done on that particular batch. But also, she couldn't do them all in one day, so she broke it out over the weekend into 2 blocks. So this is actually also blocked. So as I said, this is like the mother of all DOEs in terms of not only how it was structured by a split plot and blocked, but also all the different things she measured. Not only overall taste on a hedonic scale of 1 to 9, where 9 is the highest, but also how it appeared on a 5-point scale, how soft it was, the weight of it, and then she came up with a very innovative way of how crispy it was by adding penny after penny until the cookie would break. And that way she could get a sense of how crispy it was, because some people liked crispy cookies and some people liked soft cookies. So eventually she came up with a recipe that was heavy on butter, vanilla free, that when baked at ideal conditions scored near perfect on her overall taste. And then here's a picture of her little penny test that she did on the texture. Then in the numeric optimization, she did 2 different setups. One was for a soft cookie and how you would make the blend and bake it off for the soft cookie. Then she did a different numeric optimization going for the crispy cookie. So for that one, I would recommend you go back and look at this posting to get more details on the chocolate chip cookies. All right, and then when you go to the website, you'll be able to follow this link because there'll be a posting of the slides. All right, so show of hands, is this impressive or what? Yes? I would say definitely. Okay. I'm glad that you appreciate this, because believe me, you would like to eat these cookies that Jessica figured out how to make. But doing the experiment at home, think about that a little bit before you embark on it. Maybe something a little bit easier than what she did and not quite so ambitious. Okay, in the remaining time that I've got, I just want to mention that in the combined structure, you could also add categoric factors. Okay, so this is an experiment that we came across in the literature, and they were working on a composite material for an aircraft, and they wanted to maximize the impact and the tensile strength. And they were going to do this by varying their epoxy fiber composite with differing amounts of elastomer, but also 2 types of that, and then differing amounts of fiber, but then 3 different types of fiber, and then also varying the hardener and the epoxy resin. Now, these are not going to go from 0 to 100%, but we enter it in that way to start with, and then we subject this C and D combination to what's called a multi-component constraint, and we do this in the form of a ratio. And as a chemical engineer, I can tell you that this is very common thinking that we get from the chemists as we go into these experiments, and they're going to say that the stoichiometry of these ingredients have to be kept within certain ranges, and that's really when they say stoichiometry, the ratio. In this case, we want to make sure that we never go outside of this range of C to D, which is epoxy to hardener, of 1.8 to 2.1. Okay, so all of this is doable in Design Expert, and I'm showing you this with StatEase 360. Believe it or not, all of those requirements can be met. And so what we'll do is we'll open up this composite design, and then I'll just show you that, yes, it can be done, and it would be an optimal combined design, not only with mixture components. In this case, we don't have process factors, but we do have categoric factors, okay? So now we have our mixture components, and this is where the edit constraints is put in. And so going back to our requirements, we say that we need to have C over D kept within 1.8, 2.1. And this is, something that can be entered in, and then it convolutes that back out into two individual constraints. It's some math that's involved there. It's nothing too complicated. And then we see that it's done some adjustments to some of these ratios to make everything work. All right, and so then we put in the categoric factors. And I like using the vertical entry for that, because that way you get, coming down in columns. If you have lots of different categories, these are nominal named, different types of elastomer and fiber. We just call them fiber 1, 2, and 3, etc. So that's how that's set up, and then it uses an optimal design structure. And we end up with a recipe sheet that looks like this. And so each run in random order, we're going to mix in differing weight percents of elastomer, fiber, hardener, and epoxy resin with a certain specified type of elastomer and a certain type of fiber. And then we measure the strength properties, the impact, and the tensile. And then, we model these. And we end up, with models that are, hybrids that are done by KCV. How about that? But now the combined structure of this is not including a process factor, but rather a categoric factor, right? And these have been reduced down, and we end up with very good fits without any abnormalities. And then we can, start working at trying to, let's say, maximize the tensile strength. And this would require some work to try to decipher this, because we've got, so many different things going on here, like the epoxy resin. We could slide that around and see if that increases the impact strength. We could change the type of elastomers. Looks like elastomer 2 is better. We could change the fiber, but there could be a combination or interaction of elastomer and fiber. So there's a lot of searching that would have to go on here. So why not just go to the numeric optimization, and then you can dial up that you want to maximize the impact, you want to maximize the tensile, and then let the program come up with a solution. And so this works. If this didn't pop up a solution, that would mean that what you're trying to do is not possible. But we should already know that, by just eyeballing the data here and see what we have. In this case, we would want to make sure that we're focusing on at least getting to a minimum level of the two attributes, the impact. In this case, we want to be sure we get at least to 100. And then I've put a stretch target in here. But in some cases, it could be that once you get the impact to a certain level, that might be enough. And so you could, recognize that as a desirable ramp. If really once you got to 130 was good enough, you'd want to type that in like that, and not, allow yourself, some flexibility for the other attributes that you have. But in this case, we just put in some kind of a stretch target, I think. And the same thing for the tensile. Oh no, the tensile does have a desirability ramp that says we want it to be at least 1200, but once it gets up to 1400, that's enough. So you want to be careful when you do your numeric optimization to be realistic about that. So that's just a little sideline, a little uh, advice, for you to be practical on setting those requirements. But the main thing that we wanted to show here is that you do have the capability of combining in categoric factors. And then just for fun, this also shows you the idea of using a ratio constraint, which is a multi-component constraint. Showing off a little bit. So in conclusion, what I wanted to do with this presentation was provide some practical aspects for combining mixture, process, and categorical factors into one optimal experiment design. And then along the way, show you how this would become a lot more possible by minimizing runs via this clever KCV or Kowalski Cornell Vining combined model, and give you some thought about how that got done and why it still works and preserves, at least the linear combinations of the mixture components with the process factors. And then the idea of a split plot, which makes, these combined designs far more doable by restricting the randomization for the hard to change factor, okay, or what we call the HTC factors. In other words, we're going to group these together in a way that makes it much more easy to do it, like making the chocolate chip cookies. All right, well, I said I thought if you attended this webinar, you would expand your horizons in deploying DOE for simultaneously optimizing product and process improvement. Horizons expanded? Yes? Okay, put your hands up if you agree. If you don't, I'm expecting to hear from you, of where I might have gone off on this or whatever. Now, if you're interested in learning more about combined designs, although I do think we'd have KCV, we captured that in the Formulation Simplified when it was published, because that's the most recent book. But this is a book that shows the combined structures. It's called Formulation Simplified. Now, if you're really just looking at process situations, then the first two books are the ones that do that. Okay, so that would be the DOE Simplified and the RSM Simplified that covers the response surface methods for process optimization. So that's our trilogy, with me as the primary author. Pat Whitcomb, who founded Staties, was really the main technical guy, along with originally we had Kinley Lawrence, professor of School of Statistics at University of Minnesota. Gary Ollert succeeded him, again, professor at the School of Statistics, University of Minnesota. And then we did really well by hiring one of their graduates, Martin Beziner, who's now our president and chief technical officer. So we have our own PhD statistician, in the house, which is really nice. And Martin has picked up on these mixture designs, and oftentimes he's presenting crash courses on mixture design for optimal formulation. So that would be a follow-up for those of you that are focusing in using Staties software in particular, because it's intensive with that software, would be taking this class on mixture design for optimal formulations. It's nowadays done at a distance, and it's done in 4 half days over Zoom. And you can check our website for more information about this, or you can contact our team, workshops@staties.com. If you've got a group of people, let's say 6 or more, then I would recommend that you contact our workshops team and then set up an in-house presentation. That would really get you up to speed on this whole thing. And we do cover the combined designs in the mixture design for optimal formulation workshop. Well, that's brought me right up to the very end here. And so what I'm going to suggest then is, rather than take up more time here this morning, Central, is that if you have questions, please email me, mark@staties.com, or any comments at all on the presentation. If you liked it, I'd be happy to hear from you. If you liked it, but there were some questions or maybe some suggestions, again, send me that mark@stadies.com. Great. Well, thank you again for attending this presentation on optimal experiment designs that combine mixture, process, and categorical inputs. I appreciate your attention and the best of luck to all of you. Take care now. And I'm waving. You can't see me, but maybe just give me a little wave as you leave. And happy clapping hands. Thank you, Wolfgang, Peter, and all the rest of you guys. All right. Take care now and have a great day and have a great year here finishing off with your experiments. Take care now. Bye bye.